Make sure it's pointed at this board primarily, or that board if I start writing on it. Walk quietly around. And we are not there yet, not there yet. Started too soon.
It's cool.
All right.
I dropped it.
I know you did. I saw you.
Stop insinuating.
All right, guys, stop talking about the camera. I don't have to edit more than necessary. All right, this will work. Okay, today is October 19th, 2009, and we are doing what is called linear combinations. Linear combinations is another way to find where two lines meet. The upshot of this unit is we're going to spend a lot of time finding where two lines intersect and some time on word problems about them. Okay? This is another method to do this. Get your notes ready. And there are two rules to linear combinations. Only two rules. That doesn't mean it's simple. Okay? There are only two rules to it, which means you have to use a lot of judgment. When I only give you a two-step process, that usually means I'm leaving out a lot of stuff that you're going to have to think about while you're doing this. Those of you who love just having a rote process handed to you that'll work every single time will probably hate this lesson. Two rules. First one is, you may add or subtract linear equations from one another. And two, you can multiply an entire linear equation by any number. Rule number one, you may add or subtract linear equations from one another. Rule number two, you can multiply an entire linear equation by any number at all. Any questions on? It can be positive, can be negative, can be a decimal, can be a fraction, can be anything you want. And you're going to have to use your judgment to know when you're going to want to do that and why. Remember, the whole point of this is we're solving linear systems. Okay, that's pretty much all we're doing for a while. If you're solving a linear system, you're finding where lines intersect. It means you're finding what x equals and you're finding what y equals. Okay? Do an example that will just involve the first rule. Give me a minute to make one up. Something that would be, actually this one would be pretty simple. Okay, here are two linear equations in standard form. They're not in slope-intercept form, they're not anything else. If this were last week, what would your first step be? Amanda?
Get one of the variables.
Excellent. Like you said, get one of the variables by itself. Which one would look easier?
First one.
I'd say the y in the first equation would be my guess. Does it matter, though?
Only because it's positive.
Only because it's positive, but no, you could try and get this y, this x, or this x by itself, and you should get the same answer no matter what. But if you try and get either of the x's by themselves, you're going to have fractions, it's going to be messy. Well, here's something a little bit simpler. I'm going to decide to add these two equations together.
Didn't we learn enough for one?
I hope so. I hope this is partly review. I'm going to add these two equations together. When I add them together, I add the like terms. If they're not written both in standard form or both in slope-intercept form, you may have to do some algebraic rearranging to make sure that you can line up the like terms easily. Yes, Mimi?
Would you have y an exponent?
If it's a linear equation, you will never have an exponent other than 1 on the x or the y. So we won't be dealing with exponents with linear equations.
So would you just have 2y then?
Oh, okay. Let's see what happens here. What is 3x plus 2x?
5x.
5x. What is y plus negative y? Bless you.
Y.
0.
0.
Plus 0. One positive y, one negative y cancel each other out. What's 15 plus 10?
25.
25.
So your answer is 5.
Yeah, so I have 5x equals 5. 25, excuse me, I was jumping ahead to the answer. So x equals 5 after I divide both sides.
Is it always going to be like that? Like, there's always going to be either no x or no y? Or is it just...
Excellent question. Your goal is to make it come out this way. For my first example, I picked one where it automatically would, because I had plus y and minus y.
Okay.
So we only had to use the first rule.
I have another question.
Yes.
But it's about the substitution thing.
Okay.
Alright, you know how, like, there's, like, positive y, minus y?
Uh-huh.
Does that mean it doesn't work? The y is just 0?
With this case, the y, there's no y left. Like, you mean when I add these?
But if it's, like, substitution.
If it's substitution,
And it's y minus y. Is there just no y or is it 0?
That's going to be one of those cases where you're going to either get parallel or coincident when the variables disappear. So yeah, they would just go away. If you wind up with y minus y in a substitution, and all you have left are numbers, that's a case we talked about last week where if you get like 5 equals 5, you have parallel lines, and if you get like 5 equals 10, you have...
Coincident?
I just said it wrong. If you get like 5 equals 5, you have coincident lines. If you have like 5 equals 12, you have parallel. We're going to do an example of that. Okay, this one worked out well. We only had to use the first rule. I just wanted to go through the process. We just had to use the first rule that you can add and subtract linear equations. Why did this work out so well? Why did this one work out so nicely? What was it about these that made it... Oh, no, actually, I'm sorry. Are we done?
Yeah. No, you plug in x back in.
Plug x back in. That's right.
Find y, right?
Yes, plug x back in to find y. We were not finished. So now pick an equation to plug it back into.
The first one.
First one.
You plug in back.
Okay, we only found x equals 5. We're not done finding a solution until we also find a value for y.
But you
I thought it
really
was
found a value
combination,
for x.
not substitution.
It's to accomplish the same goal, which is solving linear systems. If you have two equations, you're always trying to find where they intersect. If you have two lines on a graph.
Y equals 0.
For this unit. Okay? So now we put 3